So then this is EE610, lecture 15. Okay. So let me consider a common source amplifier with a resistive load. So let me consider an amplifier with the input stage being constructed using a PMOS. Let's say this has been biased to some correct gate voltage VGP. And for now, I'll simply consider this as being our load, right? And I'm interested in what the small signal gain is from the input here to the output. Okay? What is the expression for the small signal gain? It's a common source amplifier. It should be GM R, right? So negative sign also, it is minus GM R. Okay. So now also tell me what is the condition to keep this transistor in saturation region. Let's say this is VDD. What is the condition that you get? So your drain voltage can go as high as VG plus VTHP, right? It can go as high as one threshold above the gate voltage, right? Which means what is VD now? That is whatever is the bias at the output, right? And what would be the bias at the output? Assume that you have biased it such that a current I0 is flowing through it. Now can you tell me what is the drain voltage? Good. So this is simply I0 into R. This has to be smaller than, what comment can you make about VGP? Sorry, this VGP. What would be the value in terms of VDD and the other transistor properties? VTH plus? Is that VGP or is that VSG? Correct. So that value should be VDD minus VSG, right? And what is VSG? That will be mod of VTHP plus root of 2I0 by mu n COX W by L, right? This plus, sorry, mu P. This plus mod VTHP, right? Which means I can say that my I0R has to be smaller than VDD minus root of 2I0 by mu P COX W by L, which means my VDD has to be larger than I0R plus root of 2I0 by mu P COX W by L. Okay. So I have two equations here. One is related to the incremental gain. The other is related to an operating point condition that we need to ensure. Okay. So now if I wanted to improve my incremental gain, I can either increase the GM, which means that the incremental current flowing through the resistor is going to increase, right? Or I could increase the resistance, which means that for the same incremental current, I will get a larger incremental voltage at the output. Okay. Now this class, we are going to focus on what happens if I increase the resistance value. Okay. Looking at the two equations given here, what do you think will happen? What happens if I increase the resistance? Let's say I increase my resistance by 10 times, right? Clearly my gain is going to increase 10 times, right? What do you think should happen to the VDD? Right? You can roughly tell me an estimate such that I am able to keep the transistor in saturation. Should I increase or decrease the VDD? I should clearly increase the VDD, right? And depending on how I choose I0 and W by L, I may have to increase the VDD by a factor close to 10, right? Not necessarily 10, but very close to 10. So let's try and observe this graphically. So So how we are going to do this is, we are going to plot I naught versus V naught. Right? We are going to look at I naught, we are going to make this V naught as a variable and plot the current through the two devices, the MOSFET as well as the resistor, as you vary V naught. Okay? So first for the MOSFET, let's say I want to plot, so this is VDD, this is V naught, and I want to plot I naught versus V naught. What does this remind you of? So finally what I want is I naught versus V naught, but what is the closest curve that you know, which relates the source to drain current with the drain voltage? The ID versus VSD curve of the PMOS, right? How does that look? So if I tell you that the transistor is already in saturation, that curve is going to look like this, right? Now then, how can I plot I naught versus V naught? What is the relationship between V naught and VSD? V naught is VDD minus VSD, right? So can you now help me plot this? You know the relationship, you know one full characteristics. Now I want to plot I naught versus V naught. How does this look? Will it be shifted up? So let's say I plotted this till VSD equal to VDD. You have to invert and then shift it. It should look like this. When V naught is equal to VDD, right, VSD is 0. Right? So whatever was happening here now has to happen here. When your V naught is equal to 0, VSD is VDD. So whatever happened here has to happen at this end. That's it. Right? So you have your PMOS characteristics in the I naught versus V naught plot like this. How does the resistor characteristic look like? So this is your resistor, this is V naught. I want to find out what is the I naught. What should I do? What is the relationship between V naught and I naught for a resistance? I naught will be equal to V naught by R. What does this represent? A straight line. So you basically have a straight line passing through the origin, and the slope of this line is, this will be equal to 1 by R, right? So the operating point is simply this. You have some V naught operating point here, right? Now let's say on top of this I give a small incremental Vi, right? Which means now my gate voltage is increasing by a small amount. What happens if my gate voltage increases by a small amount? What happens to this curve? Does it shift up or down? Gate voltage has increased, right? What happens to the current through the MOSFET? Decreases, right? So it has to shift slightly down. Let me show it with a different curve. Right? Which means the new point where it has intersected is this. Right? And what is the corresponding incremental output voltage? Is that available on this picture? What is the incremental output voltage now? It is this. Right? So now if I want to get a larger incremental output voltage for the same incremental change in the gate voltage, what should I do? What should I do to this resistance curve? Slope should be reduced, right? Otherwise I should use a larger resistance. So let's say I use something like this, right? Then the 2 points are these two. And because the slope is smaller now, because your R is large, you'll see that this is higher than earlier. Okay? Now, if I wanted 10 times the gain, I will have to use an even smaller slope, something like this. Right? But do you see a problem when I do that? Yeah, the transistor has now entered into the linear region. In the linear region, the GM has dropped, the RDS has reduced even further, and therefore your gain is going to be smaller. So in our attempt at making this R larger and larger, we have made our GM much smaller. Right? So this is a problem. Now what is the solution? Let's say I still wanted to use this value for resistance, but I wanted to ensure that the transistor remained in saturation. What can I do? I can increase the VDD. Right? That is what we saw here. So now I could say that, okay, I'll not be so adamant on having a lower VDD. I am okay with increasing my VDD. And then I can have a curve like this. Right? So now even with a larger resistor, I'm fine. But then your manager tells you, you need to get even more gain. So you decide to make your R even larger. So now your R, instead of looking like this, looks like this. Let's make it even larger, right? We are very ambitious people. So we made our R even larger, the slope reduced further. Now what do? Increase the VDD further, right? So we went on increasing the VDD. And eventually at some point, you will have to plug your transistor directly to the 220 volt socket. Is this clear? Now, of course, you can connect your transistor to the 220 socket on the wall, but your transistor is going to go poof because it's not created for these high voltages, right? These transistors are created for smaller supply voltages. Now, our aim is not to celebrate Diwali every day. Therefore, we have to now take a step back and figure out a better method. So let's take a step back and see what the real requirement is, right? So let's say the transistor properties for a reasonable VDD is like this. And given that we want to make sure that our operating point drain voltage is away from the triode region, because on top of this we'll eventually have a small signal riding, right? And we don't want the transistor to go out of saturation the moment we apply a small signal. So we would ideally like our our operating point drain voltage to be somewhere here, well away from the triode region cutoff, right? So let's say I want to make sure that the operating point drain voltage is here. On top of this, I want to make sure that the slope of the line passing through this is very small, because I want to use a very large R for a gain, very good gain. So let's say I want a slope like this, okay? Or maybe let's be a bit more ambitious and say I want a slope like this. So clearly this cannot be a resistor, right? Because if I extend this, if I assume that this is a linear element and I extend this, I see that it is not passing through the origin, right? So clearly not a resistor, plus it is passing into the second quadrant, which means that if the IV characteristics of the device is hitting the second quadrant, the device is no longer passive, right? So then this becomes an active device. Now you know that we like passive devices because active devices are a dream for the most part. So we don't want this to happen, right? Which means we will need to figure out what should happen to this characteristics beyond some point. So all that we are trying to do is, we have a PMOS like this, which is acting as our amplifier stage. It has to be connected to some load here. Earlier the load was a resistor. Now we have figured out using a resistor as a load is not very effective. So we have to figure out another block to be put in there, right? And we are now trying to figure out what the characteristics of that block should be. So we said that we have identified some point through which it needs to pass through, and it needs to have a smaller slope, and if it needs to be a passive device, then at some point it has to come down like this. Okay? So does this red curve remind you of something? Transconductance of a MOSFET, but we are looking at an I0 versus V0 curve. Does this remind you of some IV characteristics of some device? A transistor with a channel length modulation, right? In particular, what transistor should this be? It has to be an NMOS transistor, right? So if I put an NMOS transistor here, right, and so this was at some bias voltage, plus you had an incremental voltage here. This is connected to some bias voltage, no incremental voltage riding on it, and I pick up the output from here. This is some V0 plus Vi, right? Then that basically corresponds to the I0 versus V0 curve I have plotted here, right? Incrementally, at this point, it looks like there is a very large resistance connected here, right? But because this device is very nonlinear, unlike a resistor whose IV characteristics was very linear and the drain voltage, quiescent drain voltage was increasing proportional to R, the quiescent drain voltage doesn't increase proportional to the current flowing through it. Is that clear? Okay. So this is is it clear why an NMOS transistor is better as a load than a resistor? Right, so this is the circuit we are working with. Instead of connecting a resistor as a load, now we have an active load. The NMOS transistor is not active per se, it is passive. But if you look at only the incremental picture, then it looks like an active device. Okay? And this idea of using an active load, using a transistor as a load, is very commonly used simply because fabrication of large resistors is also a little complicated on a resistor, and this allows you to have a very large incremental resistance value even when you operate on a smaller supply voltage. So how does the incremental circuit look like? So you have Vi connected to the PMOS. This node is connected to ground. You have plus minus Vi. Vi appearing as the VGS of the PMOS transistor, which means the current flowing through this is Gm times Vi. I'll add the subscript P to show that it is that of a PMOS transistor. You will also have RDSP connected here. Okay. Then you have the NMOS transistor. What happens to the gate of the NMOS transistor? This is only a bias voltage. Incrementally, nothing is riding on it. Therefore, this is connected to ground, which means its VGS is 0. Current flowing through the transistor is 0. And then you have RDSN. Right? In other words, this is simply GMP times Vi flowing through RDSN parallel RDSP with Vi appearing as your input. Right? So what is V0 by Vi? This is simply minus GMP into RDSN parallel RDSP. Right? Or you can also write it as minus GMP divided by GDSN plus GDSP. Right? So another way to come at the same result is you want to connect some load here, and that load has to give you a very high impedance. One way to do that is to connect a current source, right? And a transistor biased in saturation with a constant VGS voltage is basically a current source. So if you knew that the current flowing through this is supposed to be some I1, one way to generate this VGN would be you pass a similar I1 through a diode connected transistor and then supply the same voltage. Okay, now there is nothing special about using a PMOS input stage with an NMOS active load, right? So if I can do this, so if I could connect my input to the PMOS and use an NMOS active stage, I can also repeat the same thing where the input stage is NMOS. So let's say this is VGN plus Vi. Instead of the load being a resistor, I will connect this to a constant. I will connect a PMOS transistor in saturation there, right? And this is still V0 plus your small signal V0. Now we said that the gain for the first configuration V0 by Vi is simply minus GMP divided by GDSN plus GDSP. Can you quickly calculate the gain for the second stage, the second configuration? Right, so I'll sketch the small signal circuit. So VGN is not present in your small signal circuit. You have Vi. The gate source voltage is Vi. Therefore, current flowing through this is Gm times Vi. And you have RDSN here. What happens to the PMOS transistor? The current flowing through the PMOS transistor will be 0 because the VGS of the PMOS transistor is 0. Therefore, you will only have RDSP, right? And this is connected to the ground. RDSN and RDSP are coming in parallel. Therefore, the gain is simply equal to minus GMN into RDSN parallel RDSP. Okay. So now if I show you both these circuits together, is something else striking you? In one case I have applied Vi to the PMOS side, NMOS is just under some bias condition in saturation. In the other case, the circuit looks almost similar, but Vi is applied to the NMOS side. Right? If you see these two, what is the next configuration that you would want to come up with? Right? Why not apply Vi to both? So let's try that out. So I apply a bias voltage plus Vi here. And then I apply a bias voltage plus Vi here. And then I look at what is the incremental output here. Can you solve this and tell me the answer? So how does the incremental circuit look like? So you have plus Vi appearing here. Gmn times Vi is flowing. The resistance is RDSN. Again, plus Vi appearing like this. So the current in this direction is GMP times Vi. And the resistance associated with this is RDSP. Right? Clearly, RDSN is parallel to RDSP, so I'll just show it like this. And what is the total current getting pulled out of this? So If it's not very clear, I can sketch it like this also. So you have GMN times Vi and GMP times Vi getting pulled out of the drain node into the corresponding grounds, right? Or in other words, I can simply combine both these current sources and say that it is GMN plus GMP times Vi getting pulled out of RDSN parallel RDSP. Okay. So what is the gain? This is minus GMN plus GMP times RDSN parallel RDSP. Okay. So this is again another variant of the common source amplifier, just that you are applying the input to two transistors. Okay, so we saw three configurations. Does the last one give you one more idea? You have applied the same input to both the transistors, but the bias is different. What happens if I keep the bias also the same? Is that possible? That is also possible, right? The only thing we need to check is if the two transistors are still in saturation. So let's assume that I have put the same bias as well. So instead of a separate VGP and VGN, it's some constant bias at both nodes. Now if both of these are similar bias and similar incremental voltages, I might as well short them. So I short both of them and then I give some bias voltage plus the incremental voltage. For now I'll simply call it as some large signal, a total Vi and some total V0. Right? Does this circuit look similar to you? Where have you seen this? Right? This is simply a CMOS inverter. So the very basic building block of digital circuits, a CMOS inverter, is in fact a variant of common source amplifier. Now let's figure out how the large signal characteristics of the CMOS inverter is going to look like. So in effect, I want to plot what is V0 versus Vi. And we will follow the same approach that we followed so far, which is I will assume that this V0 is free, it's a free variable, and I will plot I0 versus V0, and again another I0 versus V0. And then I'll combine both and see the result I get, right? So I first want to plot I0 versus V0. I'll do this for both NMOS and PMOS transistors. Their curves are going to intersect at some point, right? So for each value of Vin, the characteristics of NMOS and PMOS transistor will intersect. And for corresponding to that, oh, this was I0 versus V0, right? Corresponding to that intersection, you will get a V0 value, right? So for each value of Vi, you get a different intersection point in this I0 versus V0. Based on that, you can estimate what is the V0 corresponding to that Vi. And once you have this information, you can do V0 versus Vi. Okay, so please give it a try. I want you to do this for 5 values. For 0 volt, so these are the Vin values. 0, some Vin1, Vin2, Vin3, and finally VDD. And they are related like you expect in this fashion. So for the NMOS, how does the characteristic look like? When Vin is equal to 0, Vi is equal to 0, how does the I0 versus V0 curve look like? It is 0, right? It's basically the ID versus VDS curve for the NMOS. So for Vin equal to 0, your curve is here. Say this was VDD. For Vin1, this will look like this. Vin2 is here. Vn3 and finally VDD. Right? How does it look for a PMOS? So we have already seen this. You simply have to reverse and then shift. So let's start with Vin equal to 0. When Vin is equal to 0, where should the curve be? It should be the topmost curve, right? When Vin equal to 0, the VSG of the PMOS transistor is at VDD, right? So your curve will look like this. Right, and where is the intersection? It is here, right? You have to look at where the NMOS and PMOS curves are intersecting for the same value of V. Okay. Now for the next value, this is slightly lower. For the third one, we'll have somewhere here. V in 3 is somewhere here. And finally, for VDD, this is flat. Right? So now for each value of Vn, I have to find out where the currents are intersecting. So for Vn equal to 0, we said they are intersecting here. Vn equal to Vn1, they are intersecting here. Right? Vn equal to Vn2, the intersection is happening here. Vn3, intersection is here. And finally, for VDD, the intersection is here. Is that clear? Right? So now, Vn equal to 0, the intersection is at VDD. V0 is VDD. So V equal to 0, V0 has to be at VDD. For Vn1, the value is slightly lower than VDD. So if Vn1 was somewhere here, the value has to be slightly lower than VDD. This is almost midway, so I'll plot, I'll shift this position slightly. Let's say Vn1 was here and value was lower than VDD. This curve is somewhere here. The next one is here, so somewhere here. And finally, for Vn equal to 0, sorry, Vn equal to VDD, V0 is 0, so you are here. Now for values of Vn, values of Vi between 0 and Vtn, what comment can you make? How does the NMOS characteristic look? For Vn equal to 0, we said the NMOS characteristics was here, right? If the value was lesser than Vtn, the NMOS characteristics is not going to shift. It is still going to be there because it is not on, current is 0, right? Therefore, all of the intersection points are still going to be here, right? Which means your output is going to be at VDD till the value Vtn, right? Similarly, what comment can you make on this side? For Vin equal to VDD, the PMOS characteristic was here, right? When your Vn was equal to VDD, the VSG of the PMOS was 0. Therefore, the current was 0 and you were simply on the x-axis, right? What happens if you reduce this VDD? Up to what point can I reduce it and still have the characteristic of the PMOS be in this line? VDD minus mod VTP, right? So, till some VDD minus mod VTP, I am going to be in this line here. Right? Now for the remaining points, if you considered more IV curves, you will see that the plot will look like this. Right? So your plot is going to look like this. And if the curves were exactly flat here, instead of having a slope, that means if the channel length modulation was negligible, how do you think what will happen to the curve? It will become sharper and sharper. So instead of it going like this, it will become more sharper. And if you have V0 versus Vi curve, how do you find the small signal gain? You simply look at the slope, right? So the slope of this curve, which will be some negative number, is going to give you the overall small signal gain of the circuit. So negligible channel length modulation, sharper curve, meaning that you have higher gain. Okay, so I'll give you 5 minutes to revise whatever you have done in this class, and then we will have the surprise quiz after.